Hello students, welcome to the physics class. This is electrostatics and this is the 8th presentation. In this we will be dealing with the effects of dielectrics in capacitors and what is the resultant or the effective capacitance when the capacitors are connected in parallel in series, and I've given you some problems also to be solved. So the first one, the effects of dielectrics in capacitors. Now what happens when a dielectric is connected between two parallel plate capacitors? In this, I hope you know what are dielectrics. For example, mica, glass, ebonite, paper, all these comes under dielectrics. Okay. Now you have two cases in this. When the capacitor is disconnected from the battery, what happens? When the capacitor is connected to the battery, what happens? So we will see the first. When the capacitor is disconnected from the battery. Okay. So see from the diagram you can see you have two parallel plates, each of cross sectional area capital A, which are separated by a distance of d, and the capacitor is charged by a battery of voltage V0 initially, and the charge stored is Q0 initially. Okay. Now the capacitance of the capacitor is given as at the initial state C0 is equal to Q0 by V0. Now the battery is disconnected. When the battery is disconnected, see the second diagram, the dielectric is inserted between the plates. The first one, the dielectric was not introduced. Second picture, the dielectric is introduced and the battery is disconnected. Okay. Now the modified electric field, the electric field will change. The modified electric field is represented as E0 by epsilon r, where epsilon r is the relative permeability of the dielectric, or it is simply known as the dielectric constant. Now since this epsilon r is greater than 1, then the electric field E will be less than E0. So as a result, what happens? The electrostatic potential difference between the plates, that is V is equal to ED, also gets reduced. But at the same time, what happens is the charge Q0 will remain constant once the battery is disconnected. So the new potential difference V is equal to ED is given as E0 by epsilon r into D. Okay. Or you can simply write it as V0 by epsilon r, because E0 into D is represented as V0. Okay. Now we see that the capacitance is inversely proportional to the potential difference. So therefore what happens? When V decreases, C increases. Thus new capacitance in the presence of dielectric is given as C is equal to Q0 by V. Okay. On substituting, you get your value as epsilon r into Q0 by V0, or in simple words it is epsilon r into C0. Okay. Now again the condition is, since epsilon r is greater than 1, what happens to the capacitance? C will be greater than C0. Okay. The electric field will be less, whereas the capacitance will be more. Thus insertion of the dielectric constant epsilon r increases the capacitance. The point to be noted is it increases the capacitance. Therefore C is equal to epsilon r epsilon naught A by D. Now you know epsilon is equal to epsilon r into epsilon naught. Just substitute the value and you get your value as C is equal to epsilon A by D. Now to calculate the energy stored in the capacitor before the insertion of the dielectric will be given as U0. It is always initial condition will be taken as naught, U0 or Q0 or C0. Okay. So U0 is equal to half Q0 squared by C0 after the dielectric is inserted. the charge Q naught will remain the same, but the capacitance will get increased. As a result, what happens? The new stored energy is decreased. So you get your value as half Q naught squared by C, which is equal to half Q naught squared by epsilon R into C naught, or in general it is written as U naught by epsilon R. Can you get the equation? Because U naught is equal to half Q naught squared by C naught. Just substituting that and you get your value of U as U naught by epsilon R. Now again the condition is when epsilon is greater than 1, we get U is less than U naught. Thus there is a decrease in energy because when the dielectric is inserted, the capacitor spends more energy in pulling dielectric inside. The next one is when the battery remains connected to the capacitor, what happens to the circuit? So the diagram is the same. You have the parallel plate capacitors without the dielectric and it is connected to a battery. In the next diagram, you have the dielectric connected to it. So what happens when the battery is connected and the dielectric is placed? So the first equation is Q is equal to epsilon R into Q naught. I hope you know what is Q naught. Now we know C is equal to Q by V naught. So the increased charge, the capacitance also increases. So the new capacitance will be represented as C is equal to Q by V naught. On substituting, you get epsilon R Q naught by V naught. Or in general, it is written as epsilon R into C naught. However, what happens is the reason for the increase in capacitance, in this case, when the battery remains connected, is different from the case when the battery is disconnected before introducing the dielectric, which we saw in the previous equation. Now, C naught is equal to epsilon naught A by D. I hope you know how you got it, because the capacitance between a parallel plate capacitor is given as epsilon naught A by D, which we derived in the previous equations. Therefore, C is represented as epsilon A by D. Now, the energy stored in the capacitor before the insertion of the dielectric is given as U naught is equal to half C naught V naught squared. This derivation also we have seen earlier. Now, we have to note that the capacitance changes. Therefore, U will be equal to half C V naught squared. After the dielectric is inserted, the capacitance is increased. Hence, the stored energy also increases. Therefore, you get the equation as U is equal to half C V naught squared. Now, introduce the values of C, that is half epsilon R C naught V naught squared, or in general it is epsilon R into U naught. Now again the condition, since epsilon R is greater than 1, then we have U greater than U naught. So in this case it must be noted that since the voltage between the capacitor V naught is constant, the electric field between the plates also remains constant. And the energy density is given as U is equal to half epsilon into E naught squared. Okay, and epsilon, I hope you know, it is the permittivity of the given dielectric medium. Now the consolidated picture of when the dielectric is inserted, what happens to the charge, voltage, electric field, capacitance and energy when the battery is disconnected and when the battery is connected. Now when the battery is disconnected, in the first case the charge will be constant, the voltage decreases, the electric field decreases, the capacitance increases and the energy decreases. Whereas when the battery is connected, the charge increases, the voltage remains constant, the electric field remains constant, whereas the capacitance increases and the energy increases. Please note, this is a very important table in which you can understand clearly what happens when the dielectric is inserted and when the battery is disconnected and when the battery is connected. What are the changes that take place in the charge, voltage, electric field, capacitance and energy? This will come as a conceptual question. The next one is, do you know, that is in your computer. I hope from the diagram you can find out it is the computer keyboards. Now these are constructed using capacitors with a dielectric. Now you see the movable plate, you have the movable plate, the key, and then the insulator, that is a dielectric, and then you have the fixed plate. Now what happens is, when the key is pressed, that is any alphabet or anything which is pressed, the separation between the plates decreases, so which leads to an increase in the capacitance. This in turn triggers the electronic circuits in the computer to identify which key is pressed. So a dielectric, a capacitor with a dielectric is used in your computer keyboards. Yes, we shall see what is the effective capacitance when capacitors are connected in series and parallel. Now in this we are going to consider 3 capacitors, each of capacitance C1, C2 and C3, when they are connected in series connection, and what happens when they are connected in parallel connection. We are going to see the effective capacitance. So the diagrams here represent the 3 capacitors connected in series and parallel respectively. Now the point to be noted over here is, when it is connected in series, the voltage will differ and the charge will remain constant. Whereas in parallel connection, the charge will differ and the voltage will remain constant. And the other formula you should remember is C is equal to Q by V. Okay, with these two parameters, you can derive the equations for capacitors in series and parallel. So the first one, here it is V is equal to V1 plus V2 plus V3, and for parallel connection it is Q is equal to Q1 plus Q2 plus Q3. The next formula, Q is equal to CV. Now what is the value of the total voltage around the 3 capacitors which are connected in series? It is Q by C1 plus Q by C2 plus Q by C3. Whereas when they are connected in parallel, it is going to be Q is equal to C1V plus C2V plus C3V. The effective capacitance is represented as, in series connection as CS and in parallel connection as CP. Therefore, V is equal to Q by CS and Q is equal to CPV. Substitute that value, you get it as Q by CS is equal to Q into 1 by C1 plus 1 by C2 plus 1 by C3, since Q is constant. Similarly over here, CPV is equal to C1V plus C2V plus C3V. Cancel the similar terms on both sides. So you get your value as 1 by CS is equal to 1 by C1 plus 1 by C2 plus 1 by C3. And for parallel connection, the effective capacitance is C1 plus C2 plus C3. Therefore, how do you summarize? The inverse of the equivalent capacitance CS of 3 capacitors connected in series is equal to the sum of the inverses of each capacitances. That is, 1 by CS is equal to 1 by C1 plus 1 by C2 plus 1 by C3. This equivalent capacitance CS is always less than the smallest individual capacitance in series. Similarly, the equivalent capacitance of capacitors connected in parallel is equal to the sum of the individual capacitances. That is, CP is equal to C1 plus C2 plus C3. And the equivalent capacitance CP in a parallel connection is always greater than the largest individual capacitance. So, in a parallel connection, it is equivalent as area of each capacitant adds to give more effective area, such that the total capacitance increases. This is a very important question, children, and based on this you may get problems. So in the next slide, I have given you 3 problems. You can take it as a challenge and work out these 3 problems. Thank you.